6.6 Entropy change in internally reversible processes of closed system. When heat is transferred to a closed system, the internal energy of the system increases. As a result, the molecules move with high kinetic energy, and the disorder in the system increases. So in this section, we are going to relate the heat transfer to a closed system and the entropy change within the system. It is often useful to plot the process on a temperature-entropy diagram. So it visualizes the processes in the perspective of the second law of thermodynamics. An internally reversible process goes from the initial state 1 to final state 2. So the total heat transfer Q corresponds to the area under the process curve 1, 2 on a temperature entropy diagram. So total heat transfer during the process from 1 to 2 is the area under the curve 1, 2. So this is the total heat transfer during the process 1, 2. Clausius inequality is expressed ds equals delta Q over T for internally reversible process. So delta Q can be written T times ds. Take the integral on both sides. Heat transfer Q for internally reversible process is integral from the initial state to the final state of T ds. Heat transfer to a system is accompanied by entropy transfer. The sign of entropy transfer is same as the sign of heat transfer. When heat is transferred from the surrounding to the system, Q is positive, so entropy transfer is also positive. When heat is transferred from the system to the surrounding, heat is removed from the system, Q is negative, so entropy transfer is also negative. So note that there is no entropy transfer associated with work. Work is also transferred across a system boundary, but work does not accompany entropy transfer. Now let's take a look at temperature-entropy diagram for a Carnot cycle. A Carnot cycle consists of two reversible adiabatic processes and two isothermal processes. It is represented on a TS diagram by a rectangle. So this is temperature of a high temperature reservoir, TH, and this is the temperature of a low temperature reservoir, TC. And this diagram is for the power cycle. Process 2-3. It is a reversible isothermal process. So heat is transferred from a high temperature reservoir to the system, QH. The area under line 2-3 or area 2-3 AB2. Represent the heat transfer to the system during the process. So this is heat added. QH is integral from A to B, TdS, which is equal to temperature times entropy change between A and B. So entropy here is SA, entropy here is SB. Process 1-2 and process 3-4 are reversible adiabatic processes. And you also notice entropy change is also 0. The constant entropy process is also called an isentropic process. isentropic process. So process 3 to 4 and process 1 to 2 are isentropic processes. Process 4.1 is a reversible isothermal process. So heat is rejected from the system to a low temperature reservoir. So this is the area underline 4.1 or area 4.1BA4 is QL, heat rejected to the surrounding. So QL equals integration BA TdS, which is TC times SA minus SB. The net work done by the system, or W cycle, is the area 12341. So this is net work, or W cycle. It also represents the net heat transfer, QH minus QL, during the Carnot cycle. This is because the net heat transfer is equal to the work done by the Carnot cycle. So the efficiency of a Carnot power cycle is W cycle divided by Q23. So W cycle is this area, and Q23 and this is Q23. If the cycle runs in a reverse direction, it becomes a refrigeration or heat pump cycle, and you can see the process in diagram B. This is refrigeration or heat pump cycle. Let's work on an example. Water, initially a saturated liquid at 150 degrees Celsius, is contained in a piston cylinder assembly. The water undergoes a process to the corresponding saturated vapor state, during which the piston moves freely in the cylinder. So we assume there is no friction between the cylinder and the piston. If the change of state is brought about by heating the water, as it undergoes an internally reversible process at constant pressure and temperature, determine the work and heat transfer per unit of mass, each in kilojoule per kilogram. So we have a closed system. The only work involved in this process is the boundary work. We need to calculate the work per unit mass, which is the boundary work is P dV. Pressure remains constant during the process and the specific volume changes. The pressure is constant during the process. Integrations of dV equals V2 minus V1. So we use saturation pressure since the phase is saturation mixture, 4.758 bar. V2, saturated vapor, 0.3928. V1, saturated liquid, 1.0905, 10 to the negative third. Take the unit conversion. So we found the work during the process. And there are two ways to calculate the heat transfer to the system. And first, we apply the energy balance to the closed system. So Q minus W equals internal energy change. Divide the equations by mass. So Q over M is work plus U2 minus U1. The only work associated with the process is boundary work. So P times V2 minus V1. And it can be written PV2 plus U2 minus PV1 plus U1. The sum of internal energy and the boundary work is enthalpy. So enthalpy change between the saturated vapor and saturated liquid. The enthalpy change between the saturated vapor and saturated liquid at 150 degrees Celsius is here. So we use the first law of thermodynamics to calculate the heat transfer to the closed system. So another way to determine the heat transfer is to use the entropy change during the process. So Q can be written TdS, or Q over M is integral from state 1 to state 2 TdS. This is lowercase s. Temperature remain constant during the process, so T S2 minus S1. So temperature is 150 degrees Celsius or 423.15 Kelvin. Entropy change. Entropy for saturated vapor, entropy for saturated liquid at 150 degrees Celsius. So heat transfer to the closed system can be also found based on the entropy change.